Currently, in information visualization area, those who create graphs for enterprise or journals are from diverse areas as statistics, informatics, journalists, and others. But not all these professionals have the knowledge related to design techniques, visual perception, or cognitive processes. However, every graph creator wants to know the impact that their design decisions have on the observer visual perception. Let's imagine this scenario. She is Annie. She wants to present her business data, and to do this, she shows a bar chart. She presented her graph to Carl, but Carl focused his attention on the big bar, not on the small one. That one is the most important to Annie because it's fundamental data for important decisions in her company. But how to know where the observer's attention will be focused in the first time? In the area of visual perception, it has been working for years with a concept called pre-attentive processing. Pre-attentive processing is a human perception process that detects a specific set of visual attributes called pre-attentive attributes, for example, color, form, texture, and orientation, and those whose pre-attentive attributes determine what information catch our attention. How humans perceive image and chart details can impact the viewer efficiency and effectiveness on their visual cognitive process. And in information visualization, the designer can take advantage of these properties in their design to help users better understand the information presented in the graph. Back to Annie, she has selected once again to present her data in a bar chart, but she has made changes in some of design attributes, replaced color, used textures, and shifted the orientation of the graph. In addition, she has used a saliency algorithm to predict where car attention will be focused. So, in the end, she will be able to choose the right combination of design elements to meet her goal. Our objective is integrate visual cognitive concept into the information visualization design process. We intend to bring these concepts to the graph designer's environment and provide insights into how her design choices might affect the observer perception. The first approach helps graph designer in the selection of most suitable graphics to meet their data attention objective. First, the graph designer must select the data subject to be highlighted, in this example, Italy. The next step is to choose some possible color palettes, 3 in the example, that the graph designer wants to use on her chart. After that, she can execute the algorithm. For each color palette selected by her, the algorithm generates many chart combinations, changing color, orientation, and texture. The final result is composed by the chart selected by the algorithm, one per palette, whose saliency map had the highest percentage of proximity to the data selected by the graph designer. Additionally, the interface displays the saliency maps of each of those charts. Our final approach to bring saliency concept closer to the graph designer was the integration of a saliency prediction model into the design process of a data visualization system. The designer creates his graph and the application connects to the algorithm on a MATLAB server to generate the saliency map of the graph created by the designer. Every design decision that the designer makes changes the attention on the graph. In this approach, we made saliency part of the design process, and the designer can use the saliency map to validate her graph at design time. At the moment, we are doing some tests with an eye tracker to improve the saliency algorithm. Also, we are improving the algorithm to make the automatic creation of the graph more intelligent. And finally, we are making some end-user validations.